Large language models are increasingly being deployed as deep search agents, equipped with web browsing, document reading, and code execution tools. But as these agents tackle harder, multi-step reasoning tasks, a critical bottleneck emerges. They become incredibly wasteful. Standard reinforcement learning rewards the final answer, not the path taken to get there. This encourages agents to over-rely on external tools, generating long, noisy trajectories filled with repeated queries, weak clues, and observations that never actually make it into the final answer. Existing efficiency methods try to fix this by penalizing tool use uniformly. But that's a blunt instrument. It treats a crucial evidence-gathering step the same as a redundant loop. The result is often an agent that answers quickly but incorrectly, or one that refuses to dig deep enough to solve complex questions. What we need isn't just fewer tool calls. We need agents that can distinguish between interactions that build the actual evidence chain and interactions that are just noise. That's exactly what CRSP, or critical step perception, is designed to do. CRSP is a training framework that teaches deep search agents to identify evidence-critical steps and shape their policy around them. Instead of uniformly rewarding brevity, CRSP rewards precision. It preserves the steps that carry necessary evidence while pruning the rest. The framework operates in 3 tightly coupled stages: backward evidence induction, recognizer distillation, and efficiency-aware policy optimization. Let's break down how it actually works. First, you need a reliable way to label which steps in a search trajectory are truly critical. A straightforward approach would be to ask a strong teacher model to read a completed trajectory and extract the critical steps. But deep search trajectories are long, noisy, and context-heavy. Direct extraction places an enormous burden on the teacher's long context understanding, leading to unstable annotations. CRSP solves this with backward evidence induction. Instead of analyzing the trajectory forward, the teacher model traces it backward from the final answer. Starting from the last tool interaction step and moving to the first, the teacher evaluates each step in isolation, conditioned on the question, the final answer, the current step's observation, and the set of future steps already confirmed as critical. A step is labeled critical if it provides or preserves evidence that was actually used downstream. If the same evidence was already captured more directly in a later step, the current step is marked as redundant. This backward pass decomposes a global extraction problem into a series of local, stable decisions. It forces the teacher to focus on marginal evidence contribution, rather than reconstructing the entire evidence chain from scratch. But running a massive teacher model backward over every single step during training is computationally prohibitive. You can't afford an n teacher call per rollout. So CRSP distills this backward reasoning behavior into a lightweight critical step recognizer. This student model is trained via supervised fine-tuning to ingest a full trajectory in a single pass and output a structured list of critical steps. It learns to reproduce the teacher's backward judgment without the stepwise overhead. At inference time, the recognizer analyzes any trajectory once, making it fast enough to deploy during policy optimization. Now, how does this perception actually train the agent? CRSP integrates the recognizer into the reinforcement learning loop using group relative policy optimization, or GRPO. Standard outcome-based RL only gives a binary reward for answer correctness. CRSP augments this with an efficiency-aware reward computed from the recognizer's predictions. For each successful rollout, the recognizer counts the predicted critical steps, K, and the predicted redundant steps, T. The efficiency reward is then formulated as a ratio. K divided by K plus alpha times T alpha is a tunable coefficient that controls how strongly redundant steps are penalized relative to critical ones. This reward scales with the proportion of evidence-critical interactions. It naturally favors trajectories where most tool calls carry actual evidential value, while still allowing longer trajectories when additional steps contribute useful evidence. Crucially, this efficiency reward is only applied to rollouts that already achieved the correct answer. The agent is never rewarded for being lazy. It's rewarded for being precise. Unsuccessful trajectories receive 0 efficiency bonus, which prevents the policy from converging to short but incorrect search paths. The results on deep search benchmarks like BrowseComp and HLE Verified are striking. Starting from the same baseline policy, CRSP maintains competitive final answer accuracy while reducing average interaction turns by 15.1% on BrowseComp and 33.2% on HLE Verified. But raw turn reduction doesn't prove the model understands evidence. It could just be learning to skip steps. CRSP validates this through trajectory intervention. Researchers take trajectories from a baseline policy, remove the final answer to prevent leakage, and then let the model continue generation under 3 different contexts: the full trajectory prefix, only the predicted critical steps, or only the predicted redundant steps. When given only the critical steps, the agent maintains accuracy close to the full context baseline while completing trajectories with significantly fewer turns. When given only the redundant steps, accuracy plummets, and the agent actually takes more turns trying to recover the missing information. This asymmetric effect proves the recognizer isn't just counting, it's identifying the actual functional evidence chain. There's also a delicate balance in how the reward is shaped. The alpha coefficient governs the accuracy-efficiency trade-off. If alpha is too low, redundant exploration is barely penalized, and the policy retains noisy trajectories that inflate both cost and failure rates. If alpha is too high, the agent starts pruning necessary exploration and accuracy drops. Crisp's optimal setting sits in the middle, removing redundancy without eroding the evidence chain. This moderate penalization is enough to realize most of the efficiency gain, while preserving the agent's ability to explore when it actually matters. You can also see this shift in tool use behavior. On BrowseComp, Crisp reduces broad search calls while increasing focused document browsing. It's not calling tools less. It's reallocating interactions toward tools that are more likely to yield evidence once candidates are retrieved. On HLE Verified, it reduces search, browsing, and code calls simultaneously, reflecting shorter, more concentrated information needs. Because trajectories are tighter and more selective, failure rates from context overflow and max-turn limits actually decrease by over 20%. The agent becomes more reliable, not just faster. Crisp represents a fundamental shift in how we train agentic search systems. Instead of treating the agent as a black box optimizer that blindly minimizes cost, Crisp treats it as an evidence-driven reasoner. By teaching models to perceive critical steps, we get agents that are faster, cheaper, and just as reliable. This is a practical, scalable path toward deep research systems that don't burn compute on dead ends. If you're building or researching efficient search agents, this framework offers a clear blueprint. Define criticality by evidential contribution, distill that perception into a fast recognizer, and shape your reward to preserve the evidence chain while pruning the noise. The gap between capability and efficiency isn't a trade-off. It's a signal processing problem. And Crisp shows us exactly how to tune it. Let me know in the comments how you're handling trajectory efficiency in your own research or deployments, and I'll see you in the next one.